All right, so today I'm going to talk about relative Turan numbers of hypergraphs. And all of this is going to be joint work with Josh Ni and Jacques Verstraete. So to start, we're going to consider a family of R-uniform hypergraphs, called R-graphs for short. And we'll say that a hypergraph H is F-free if it contains none of the elements of this family F as a subgraph. And the central object we're going to kind of be looking at is the Turan number, which is denoted by X and F. This is the maximum number of edges in F-free R-graph on n vertices. This is a very classical object in combinatorics, and it dates back to Mantel, who originally proved that the extreme number, or the Turan number for the triangle, is n squared over 4. In other words, if you have a graph that's triangle-free on n vertices, it has at most this many edges, and there exists a graph with exactly this many edges, namely a complete balanced bipartite graph. So that's a very classical result for graphs. And you can ask, what happens for hypergraphs? And the first thing you have to figure out is what's the correct definition of an R-uniform triangle. And there turns out to be several non-equivalent ways to define it. To start, we'll be considering the notion of loose triangles. And more generally, we'll define the loose L cycle, the loose L uniform, the loose R-uniform L cycle, CLR, in this way here. But it's easiest just to see this by picture. So here's the 3 uniform loose triangle, which you can think of as being formed by taking a graph triangle and then inserting a new vertex inside each of its edges. And more generally, you can define the loose cycle by inserting r-2 distinct vertices inside each of the edges of a graph CL. An important thing I want to highlight here is that when r is at least 3, the triangle, the loose triangle, is 3-partite, or r-partite, I should say. So in particular, this coloring shows that the 3 uniform triangle is 3-partite. And this is very different from the graph case because the graph triangle is not bipartite. And because of this, the Turan problem is very different for r greater than or equal to 3 versus the classical r equals 2. And in particular, Frankel and Ferretti showed what the Turan number is. It's n-1 choose r-1 for r greater than or equal to 3 and n sufficiently large. And the extreme example for this is the star hypergraph, which consists of all R sets, which contain some common vertex. And it's not too hard to see that this is going to be triangle-free, and it's also going to have this many edges. So the difficult part is showing that this is an upper bound. And I'll note that in general, very little is known about hypergraph Turan numbers. It's a very, very difficult subject. So naturally, when you have a very difficult problem, you're going to try and generalize it to make it even harder. So to that end, we're going to generalize the Turan number in the following way. So again, we're going to be given a family of R-graphs F, and we're also going to be given a new thing, an R-graph H, which we'll call the host hypergraph. And we'll then define the relative Turan number, XHF, to be the maximum number of edges in an F-free subgraph of H. So an example of this is that I claim that the relative Turan number for KNR, which is the complete R-graph on n vertices, is equal to just the classical extremal number for F. And this is because any F-free subgraph of KNR is just going to be some R-graph on n vertices and vice versa. So we have that correspondence. And so again, as I mentioned before, determining these quantities exactly or even close to exact in general is much too hard of a problem. So what we want to try and do in general is we're going to take our favorite family of hypergraphs F, and what we're going to try and do is determine some general lower bounds on this quantity here, the relative Turan number, based on certain natural parameters of H. And for this talk, the parameters we're going to use are the number of edges in H, which is how many edges we start with, and the maximum degree of our host H, which I'll denote by delta. So let me show a brief example of kind of what we're looking for. So if our host is the complete graph Kn, then as I mentioned up there, the relative Turan number is exactly the classical Turan number. But we want to write this in terms of the number of edges we started with, which is about n squared. So we can divide by n squared and multiply by n squared to get that this is approximately here. But again, we don't want the order of h, we want the maximum degree, which fortunately is also about n here. So we can just replace these n's with deltas and get this bound here. So these are the kind of bounds, or bounds like this is what we're looking for. And in particular, what this brief argument shows is that if we want a bound of this form, the strongest bound we can prove is in fact this as a lower bound. And that's precisely because the clique shows that such a bound would be best possible. And it was conjectured by Foucault, Krailovich, and Peranu that this bound is always achievable. In other words, for any family of graphs F, if we have a host with maximum degree delta, then you can achieve a lower bound of this form. And roughly what this says is that they conjectured that for every family of graphs F, the clique is the worst host, at least in terms of order of magnitude. In that, again, the clique always has this bound here. And what this is saying that you can always do at least as well as the clique for any host with these properties. It was a fairly broad conjecture, and Perano and Reed managed to prove that was true in a number of nice cases. So in particular, they proved it's true if you're looking at a single F, which has diameter at most 3. They also proved it's true if you look at all the cycles of length up to L, and a couple other families of graphs. And in particular, I'll highlight that they were able to prove this result despite, in many of these cases, us not knowing what the classical Turan numbers are in these cases. So for example, it's a very famous problem, an open problem of Ederson and Simonovitz to determine the classical Turan numbers of the cycles up to length L. And we still don't know what that is, but nevertheless, Turan and Reed were able to prove that you can get a lower bound of the form in terms of the classical Turan number of this family, whatever that might end up being. And again, the clique shows that the bound is sharp. So that's roughly what's known for graphs. And now we want to move over to hypergraphs, where again, one might conjecture that the worst host should always be the clique. So kind of motivated by this thought, if we look at the loose triangle, the 3 uniform loose triangle, and we take our host to be the clique, then Frankel Ferretti gives this, which you can rewrite in this language here. And because of this, you might conjecture that you can get a lower bound of this form. And this turns out to be basically true. In particular, I proved with Josh Shimi and Josh Strada, if you give me a 3-graph H with maximum degree at most delta, then you get a lower bound of the form delta minus 1.5 minus little 1 times the number of edges we start with. So this is basically showing this bound is tight up to this little 1. Now I'm going to go and sketch the proof of this. And the rough idea is we're going to be given some hypergraph H, our host, and we have no control over this. Then the way we'll try and find a subgraph for it in general is we're going to fix some nice triangle-free 3-graph J and try and make our subgraph of H look like J, regardless of whatever H looks like. And roughly this idea was also used by Toronto and Reed. So with that in mind, let's fix some triangle-free 3-graph J, which we'll determine later. What we'll do is we'll start with a random mapping from the vertices of H to the vertices of J. And roughly speaking, what we want to do here is we want to say if some vertex U in H maps to some vertex V over in J, then we want in the subgraph H prime for U to play the same role as V does in J, roughly. And to be a little more precise, we're going to, as a first attempt, we're going to take our subgraph H to keep all the edges E and H such that the edge E maps onto an edge in J. In other words, if V1, V2, V3 are the edges, the vertices of E, then the image set of these vertices is an edge in J. And we'll see an example of this in a second. But unfortunately, this kind of naive idea isn't good enough to get through to make sure that H prime is triangle free, even if J itself is triangle free. So as kind of a silly example, if J consists of a single edge on vertices 1, 2, 3, and if H is just a loose triangle, then if Chi happens to give the assignment 1, 2, 3, 1, 2, 3, then this edge, for example, maps onto an edge J and J. This edge and this edge also have this property, so all 3 edges are kept in H prime, and in particular, H prime contains a triangle. So that's no good. So again, here's the issue. And we'll get around this particular issue by adding further restraints on which edges we keep. So again, we'll keep an edge if 1, it maps onto an edge in J. And the second key condition we'll need is that we further require that if there's another edge F which intersects E in exactly one vertex, then F and E map to distinct edges in J. And this solves this exact problem here, because if you look here, if this is our edge E, then it satisfies 1. It maps onto an edge in J, as we saw before. But there is another edge F, which intersects in exactly one spot, which maps onto the same edge in J. And therefore, according to rule 2, we would not keep edge E. And in fact, we would keep none of these edges. So this solves this particular problem. But unfortunately, it's still not good enough to make sure that H prime is triangle-free. So in particular, if our host J is the star graph, which is the extremal example, so probably what we should take, at least naively, then I claim that this coloring also works and makes a loose triangle. So if H is this thing here, and J is the star, then each edge here passes test 1, because each one maps onto an edge in J, i.e. it maps onto an edge containing the vertex 1. And further, each of these map onto distinct edges of J. So 2 is definitely passed here for each of them. So we still have problems. Again, this is the problem. So you might try and get around this by adding some like third condition, where maybe you just don't require, you force edges that intersect in one vertex to not intersect at all. There are many things you could try. None of them seem to work if you force further conditions on H prime. So what you can do instead, though, is you can force stronger conditions on J. So again, J at this point always specifies that some triangle-free 3-graph. And it turns out if you force it to J to forbid other subgraphs and not just triangles, in addition to triangles, then you can avoid this picture here. And in particular, the kind of template J that we're going to want to pick is a construction of Ruza and Semeretti, which is a T vertex 3-graph, which has T squared minus little 1 edges. So this is almost extremal. The optimal is really T squared, so that's a little suboptimal, but still pretty close to extremal. And this is going to be triangle free. Well, that's not too helpful because the star also has this property. But the key extra insight is that this 3-graph is linear. In other words, any 2 edges intersecting at most 1 vertex. So now let's try and do our procedure where we now fix our template to be distributed Semeretti construction for some T, which we'll determine later. And again, we'll start with some random mapping from H to J. And again, we'll define our subgraph if they pass these 2 conditions. And we claim that with this, finally, our subgraph is going to be triangle free. And so let's go and prove this. So assume for contradiction that E1, E2, E3 survive in H prime, and they form a triangle in the following way, in such that they pairwise intersect in these vertices xij, which are all distinct. And I'll note that because xij is in the image of each of ei and ej, by definition of how we define this, wherever xij maps into will also be in the pairwise intersection of these 2 edges here. And further, I claim that these 3 vertices must be distinct. And the way to see that is that if, say, x12 and x13 map to the same vertex in J, then because both these vertices are in E1, its image set would have size at most 2. And this contradicts it 1, where it maps onto a 3 set of J. All right, so we have these 3 all distinct. And furthermore, I claim that the pairwise image of the pairwise intersection of these image sets, it can't be 2, because both of these are edges in J, and because J is linear, there exists no edges which pairwise intersect. And further, I claim that they don't pairwise intersect in 3 places. In other words, these 3 edges are all distinct. And that's because of rule 2. Each of these, every pair of these edges intersect in exactly one place because they're a loose triangle in H. And therefore, if they survive, they can't map to the same edge. So these 3 things are all distinct. So in particular, we've concluded that there's this vertex in its intersection, and that it doesn't intersect in 2 or 3 places. In other words, the intersection must be exactly this vertex wherever chi of xi is. And these 3 vertices are all distinct. And if you look back on the definition, this is exactly how you define a loose triangle. So this is a loose triangle now in our template, RT. But this contradicts the rules of summary construction being triangle free. So we conclude that H prime is indeed triangle free. Okay, so again, here's our setup. And we've now just shown that with this setup, our subgraph that we get is always triangle free. So to complete the result, we need to show that this subgraph has many edges, at least in expectation. And by linearity of expectation, it's enough to just consider any edge E and ask what the probability is that it continues to survive in H prime. So first, to survive, it needs to pass 1. It needs to map onto an edge of J. And I claim that this probability is exactly this quantity. And the reason is the number of ways that E can map onto J is exactly T cubed, because each of its vertices has T places it can go. And then there's roughly the number of edges in J, ways where it can survive and map onto an edge of J. And this is true up to permuting the vertices. And because J is this Riese symmetry construction, the number of edges, this probability is exactly T to the minus 1 minus little. All right, so given that an edge E passes test 1, we claim that if there's an edge F which intersects in exactly 1 spot, then the probability that they map to the same edge is at most this quantity. And the reason for this is because F has 2 vertices now, which are not in E. And in order for this to happen, in particular, these 2 vertices have to end up in this vertex set. And for any given vertex, there are 3 places that it can map to land in here out of the T possible places that it's going to end up. And it's independent whether each of these vertices ends up in the center. So the probability then of just simply having chi of F be a subset of chi of E is at most 3 over T squared. In particular, this probability of being equal is at most. And the number of bad edges F which intersect E in exactly 1 spot is at most 3 times the maximum degree in H, because each vertex in E is intersected in 1 spot by at most the number of edges that contain that vertex, which is the maximum degree. So if we just take a union bound over this bad event of 2 of these edges mapping to the same edge, we get that the probability that 2 is satisfied is at least this quantity here. And if you do some optimization, you can take T to be about delta to the 1/2 to get that this probability is at least a half. And in total, putting this together, the probability that an edge survives in the subgraph is going to be at least the probability it passes 1, which is T to the minus 1 minus little 1, times probability that passes 2, given that passes probability 1. And this is at least a half. And plugging our value for T, this is about delta to the minus 1/2 minus little 1. So in total, by linearity of expectation, the expected number of edges that in total survive in H prime is at least this quantity here. And to conclude the result, we just note that as a standard probabilistic argument, because this holds in expectation, in particular, there must exist some H prime with at least as many edges formed in this one. So that proves that H always contains a subgraph with at least as many edges as desired. And there are a couple ways you can kind of generalize this approach. The first is just to triangles of larger uniformity. And in this case, almost the exact same proof works as before, and you get this bound here. The only slight change is now instead of using a linear 3 graph which avoids triangles, you use a linear 3 graph which avoids, or sorry, a linear R graph which avoids triangles. And this exists because of work of Erdős, Frenkel, and Röbel. And as in the R equals 3 case, we know that this bound is tight up to this little 1 term. So it's natural to ask, is this best possible? And it turns out we don't know. The best upper bound we can prove is we can show that there exists an R graph H, which has an upper bound of delta to the minus 1/2 times the number of edges we study. An important little thing I'll note with this result is that this host that we take here is not the clique. If you do the clique, you'll get a much weaker bound than what we have here. So this shows that this conjecture of Fagode, Peranu, and Grigorevich does not hold for hypergraphs. In other words, there are families of hypergraphs, in particular triangles with large uniformity, where the host is not, the worst host is not the clique. So it seems that the hypergraph, as in the case for the classical Turan problem, the relative Turan problem seems to be a lot different for hypergraphs. So that's how you can extend these results to other triangles. But what about other families of hypergraphs F? And you can try and do similar approaches, and sometimes it works, but you'll definitely have to tweak the approach. So one example where this kind of method works well is K22S, which is the complete three-part type 3 graph with parts of sizes 2, 2, and S. And the reason we look at this kind of perhaps strange-looking example is that if S is sufficiently large, we know what the classical Turan number is. It's exactly n to the 3 minus a quarter, which in our relative Turan language can be written as this, with our host being K and 3. And this result follows by methods of Book and Conlon using random polynomials, and explicitly it was done by Ma, Yuan, and Zheng. So, all right, so yeah, with K22S, we have this particular construction of the clique, giving delta to the -1/8 as our kind of decay factor. But we can do better than this. So we prove with chalk. There exists a 3 graph where you can get a decay factor of delta to the -1/6, which is strong. And moreover, we prove that this is essentially best possible. Again, you can get a lower bound of delta to the -1/6 minus some little 1 term times the number of edges we started with. And I'll note that more generally, we have results for any R-partite R graph, provided we have certain knowledge of the classical Turan numbers. But for simplicity, I'll just state it as this one. So the proof is similar to the loose triangle case, but there are some subtle differences. In particular, one critical change is that we now need to break the proof into 2 cases. One where our host H has small codegrees, and the other where it has large codegrees. And this will kind of come up naturally in the proof. All right, so let's do this, and let's first just naively try and adapt our random homomorphism approach that seemed to work well for so to do this, we fix some K22S free 3 graph J on T vertices, and we'll randomly map the vertices of H to the vertices of J. And as before, we'll keep each edge under 2 conditions, the first being that it maps onto an edge in J. And this slightly different condition we now need is that we also require that if F intersects E in exactly 2 places, then they map to distinct edges. So before with loose triangles, we required this to hold when they intersect in 1 place, but now we require it when they intersect in 2. And kind of the motivation for this is for loose triangles, the only way you're going to end up getting a loose triangle in your subgraph is if you had 2 vertices intersecting in 1 spot, which both survive, because in the loose triangle, all its edges pairwise intersect in 1 spot. But now with K22S, its edges can pairwise intersect in 1 or 2 places. And it turns out that really we only have to care about them intersecting in 2 places. And the case where they intersect 1 edge is, or 1 vertex is kind of swept under the rug in the injection argument. Let's ignore that. So one can check, if you go through kind of the same argument we did before, that with this setup, our graph will be K22S. In particular, we don't have to impose any initial constraints on J like we did before, forcing it to be linear. Just being K22S free and having these conditions is enough to guarantee that our subgraph is going to be K22S free. So now it remains to compute how many edges we get. And if you look back at the analysis we did before, our old condition of having dealing with edges which intersect pairwise in 1 vertex, that forces us to take our number of vertices T to be about delta to the 1/2. And this was roughly because for every fixed edge E, there were about delta edges which could intersect it in exactly 1 spot. And for any one of these edges F, it had probably about 1/T² of mapping to the same edge in E. And that was because there were 2 vertices in F not in E, and each of them had about 1 in T probability of mapping in T. So if you follow that logic through with our new setup, you'll see that we now need to take T to be about delta sub 2, which is the maximum codegree of H. This is because, again, you take any edge E, and there's at most deltas of 2 edges intersecting it in 2 places. And for each of these, there's one vertex which now needs to map into E. So its probability is 1 over D of E. So again, if you follow these computations through to the end, you'll get the following lemma, which says that if you have maximum code degree at most D, and if we happen to know the classical Turan number is this function here, then you'll get a lower bound of this form. And in particular, if you want to prove a lower bound of the form delta to the minus 1/6, then this will work as long as D is not too large, in particular if it's not larger than delta to the 2/3. But you need a new approach if our host has large code degrees. And in particular, you want to somehow exploit the fact that we now have large code degrees to get a stronger bound. So one lemma you can prove in this direction is the following. So if the enemy gives you a host which just so happens to be 3-partite, and further such that every pair in B1 and B2 has either code degree 0 or D, then you can prove a lower bound of this form. And in particular, I'll note that here, the exponent in D is positive, which differs from here where it was negative. So here, large code degree means a worse bound. Here, it means a better bound. So here, we're really exploiting that we have large code degrees to get a larger bound. And I won't go through all the details here, but roughly the idea is you look at the pairs in B1, B2, and whether they have code degree 0 or code degree D, and you define a graph where the edges are those which have this large code degree. And then in that graph G, you can use results of Turan and Reed to find a large C4-free subgraph of this graph G. And then you can lift this graph, which lies in B1, B2, to all of H by just taking all the edges which contain each edge of this subgraph in H. Many words, it's not too hard, technically speaking, to prove this. And if you do the numerics, you'll end up getting this bound here. And roughly speaking, if you lose a little one term in your bound, you can always take any H, roughly speaking, which has large code degrees and reduce it to roughly this case. So with this, we can very roughly, and I'm lying to you slightly, but it's morally correct. If H has maximum code degree D, then we get these two bounds, one in the low code degree regime of D to the minus 1/4, and in the high code degree regime of delta minus 1/2 minus little 1 times D to the 1/2. And with this, you'll get a lower bound of delta to the minus 1/6 minus little 1. Again, if you're smaller than delta to the 2/3, you'll use this bound, and if you're larger, you'll use this bound. And this proof actually gives a little more information. It shows that if you thought this bound was tight, which it turns out to be, then the only way the construction that you need to consider must have maximum code degree about delta to 2/3. If it had smaller code degree, this first bound here would give a stronger bound than delta to the minus 1/6. And if it had a larger code degree, then this bound would give a stronger improvement. And possibly the first thing you might think of to just try and cook up some R graph or 3 graph which has kind of code degree would be an unbalanced complete 3-partite 3 graph. And indeed, this turns out to work. If you take 3-partite 3 graph with parts of size n and n squared, then its relative Turan number turns out to be this form, giving the matching upper bound. And very roughly, this proof uses super saturation result for graph C4s. But I won't go into the technical details here. Right. So those were kind of the 2 main results I wanted to highlight. And now I'll just briefly sketch a couple other results that you can prove in this direction. So we saw results for loose triangles, and you can ask what happens for other loose cycles. And the answer is we really don't know. So for 3 graphs, we can prove, so we have bounds for general R graphs, but for simplicity, I'll just say for 3 graphs. And for any L, we can prove a bound of this form here, delta minus 1 plus 1 over L. And in general, we don't have very good upper bounds. If L is even, we can get a pretty effective bound, which is of this form delta minus 1 plus 1 over L minus 1. But there's still a significant gap here. And we suspect that the lower bound is closer to the truth. And I'll also note that, again, we have bounds for larger R, but very quickly the gap becomes very wide between these two quantities. And also for odd L, we have very few results on anything meaningful for upper bounds. And I'll also note that, so the lower bound comes from, roughly speaking, a counting argument, being a little more clever than that, but nothing too sophisticated. And the upper bound mainly just relies on a result of Mbaye and Yefreman, proving bounds when H is a random hypergraph. It turns out when you choose the correct model of random hypergraph, you can get a bound of this form for the loose, for even loose cycles. So that's what we know for loose cycles, and again, there's some pretty big gaps in our knowledge. But we can do a bit better for other kinds of cycles, namely for Baire cycles. So we'll define F. We'll say that a hypergraph F is a Baire cycle, CL. It has L distinct edges and L distinct vertices, such that the ith vertex is ith of these vertices is in the intersection of EI and EI plus 1 with these written cyclically. And we'll let BLR denote the set of all R uniform Baire L cycles. So kind of a trivial result here is that if your uniformity is larger than your cycle length, then the relative Turan number can be you have a lower bound of the form delta minus 1 times the number of edges you start with, and this bound is possible. And so why do I say this is trivial? Well, the lower bound follows by us taking a maximal matching in H, and more generally, for any family F which doesn't contain a matching, this will in fact always give a bound of this form. And this is best possible because you can take H to consist of delta edges, all containing a common set of size L. This has maximum degree delta, and because R is greater than L, this thing actually exists. And you can check that if you take any L edges of H, because they contain this common set of size L, that defines a Baire cycle, and so you lose. So you can only take constantly many edges in H, and particularly you get an corresponding upper bound. So when R is bigger than L, you can't really say anything interesting here. But when R is at most the size of L, there are cases where you can say something interesting. So in particular, we have the following type bounds for these cases of Baire cycles, and they're typed by considering the clique as your host graph. And the reason we look at these at first glance kind of random looking set of examples is because these 4 examples, so there are very few cases where we know the classical Turan number for Baire cycles, and the only cases are those covered by this theorem or by this theorem, or rather, every case is either covered by this proposition, and those that aren't are only these 4 cases, and they're covered by this theorem. And we have a result that's slightly more general than this, which says that if the Turan number for certain families of Baire cycles is what we think they might be, then you can prove a type bound here by taking the clique to be the host. So those are what I want to say. So these results all cover worst case bounds, for bounds that work for any arbitrary H that the NV gives you. But you can also consider what happens for the average case, or for random hosts. So to this end, we define HNPR to be the random R graph on N, which includes each edge, or each of its R sets independently and with probability P. So here, we can also get type results in a number of cases. So for example, for K22S, or more generally for any R-partite R graph where the Turan number is what we think it is, we can prove essentially type bounds up to some little 1 factors in the random host. And here, the lower bounds are, roughly speaking, following either from the random homomorphism bound that we had before, or from a simple deletion argument in the smaller region. We can also prove bounds for Baire cycles. So in particular, and really we look at the girth problem here. So if we happen to know bounds on the classical Turan number for all of the cycles up to length L, then we can prove the following bounds on the Turan number in the random R graph, or 3 graph in this case, when P is sufficiently low. And there's a couple things I want to note here. The first is that the bounds are not tight. So here we have a 3, and here we have a 2. So there's still a significant gap here. One benefit, or one nice thing about this theorem is that it's relatively easy to prove the upper bound. So again, the lower bound follows from our random homomorphism machinery, and the upper bound, as is often the case here, follows from the method of hypergraph containers. And typically, these kind of bounds are rather technical and numerical heavy. That was certainly the case in proving that these bounds here were tight. But to prove these upper bounds is very short, like 10 pages, roughly speaking. And it just basically, it reduces the problem for finding this extremal number in 3 graphs to finding this extremal number in graphs. So we can just use some heavy machinery developed by Morris and Sexton to get this upper bound here. And another thing I want to comment is that we didn't talk about this girth problem of avoiding all the cycles up to length L before, because it was trivial in the general case. And that's because if you just look at B2R in particular, then our proposition from earlier shows that we get a trivial bound here when we look at this sunflower containing a common pair of vertices. So in particular, this result highlights that you can get some interesting results. Even if you can't get interesting results for general hosts, you can still get some interesting results for random hosts, for example, or maybe other kinds of hosts. And lastly, I'll note that we can actually improve this lower bound here when L equals 3. So returning back to triangles, if we want to find a subgraph of H and PR, which is linear and has no triangle, then we have essentially tight bounds up to these little 1 factors here. So here we improve the lower bound from this theorem. It's unclear at this point whether that should be possible in general or if it's just something special for L equals 3. But in any case, it's nice we can do this, and we can do this for all R as well. And I'll note that you get the same lower bound if we forbid a smaller family of cycles, namely if we avoid just all Bayes triangles or even just the loose triangle. And these bounds and the upper bounds continue to hold when R equals 3. So we have tight bounds in all 3 of these cases. But when R gets larger than 3, then just avoiding B3 or just avoiding the loose cycle, the gaps become fairly wide. Yeah. And there are a lot of open problems left in this area. So in particular, kind of the first question I wanted to ask is the little one term necessary in the bound on our lower bound for loose triangles, and similarly for everything else, which we had a little one term. We think maybe not because of the intimate connection between loose triangles and arithmetic progressions, but it's unclear. Another thing to ask is we have bounds for loose cycles, but again, they're fairly wide, and especially for R large and L odd. So we'd like some tighter bounds there. And we think that possibly, at least for R equals 3 and L even, that one can maybe get tighter upper bounds by further improving bounds for the random hosts for loose. And then also, again, we have fairly large gaps for random hosts and the girth problem of avoiding all cycles of L. So that would be good to improve there. And of course, the problems are endless, really. You can just pick your favorite family of Hypergraphs Fs and your favorite family of possible hosts, whether random or generic or something else, and ask what kind of bounds can you improve. So there's still a lot to do here. And with that, I'm going to end the talk.